This video alternates between going through the math and theory and drawing the gears. The formula sheet and diagrams are linked in the description below. To get started, involute gears have teeth made by involute curves. Involute curves are defined by what we would call the base circle in this context. The most fundamental aspect of any spur gear is its pitch circle. Notice how the pitch circles of these two gears, the dotted blue lines, they converge together in the middle, and they're tangent to each other at this point, known as the pitch point. Around the pitch point, we can define the pressure one tooth exerts on the other, and therefore the shape of the involute curve. This gives us a common tangent and a common normal. In this video, we're going to be assuming a pressure angle of 25 degrees, though 20 degrees is also very common. The addendum and dedendum, A and D subscript D, that's going to be the distance from the pitch circle to the addendum circle and dedendum circle, respectively. As for the base circle, that was mentioned before, that's where the involute curve is going to come from. Specifically for the base pitch and circular pitch, these arc lengths define the module, or the unit of measurement defined by the ISO for the size of the teeth. So say that I had two axles that I wanted to connect with gears, and these two axles, they're going to be spaced 90 millimeters apart. That gives me a center distance C of 90. And let's say I also want to define a gear ratio between these two gears. So I'll make the left one the bigger gear, and then the right one the smaller gear. The smaller gear is usually called the pinion, while the bigger one is just called the gear. So let's give this an angular velocity ratio MV of 4:3. An angular velocity ratio is the ratio of the angular velocity of the output gear divided by the one of the input gear. D stands for the pitch diameter, and Z stands for the number of teeth of each of the gears. I can also refer to MT, the torque ratio, and that's going to be, as you can see, an exact reciprocal of MV. In my case, that's going to mean that I'm going to have a torque ratio of 3:4. Now, as for deciding the number of teeth based off of this ratio, it just has to be a multiple. So I'm going to multiply everything by 4, and I'll give my gear 16 teeth, and I'll give my pinion 12 teeth. So from this information, we now want to find the circular pitch P. Because P determines the module, we need our teeth to have the same module in order for them to mesh. So P is going to have to equal the circumference of the pitch circle, so that's 2 pi d over 2 divided by the number of teeth, z. We can simplify that down to pi d over z. And now we can isolate d instead, so we get that the pitch diameter is equal to pz over pi. Now, what do we know about the center distance over here? Well, we know it has to be the radiuses of the pitch circles added up. So that's going to be d1 over 2 plus d2 over 2. Now we can plug in what we just found into that equation. So what we're going to get now is pz over 2 pi, and I'll get that subscript 1, plus pz2 over 2 pi. So now let's factor out the p. So we're going to get p parentheses z1 plus z2 divided by 2 pi, end parentheses. And we can now get that p is going to equal 2 pi multiplied by c divided by z1 plus z2. And we know all the information, so we can just plug it in, and we're going to get 20.20 millimeters in this case. So now that we found the pitch, we can plug this in to find the pitch circles in the module. So when I plug that into the first pitch circle with 16 teeth, I'm going to get around 102.86 millimeters. For the pinion, I'm going to get a pitch diameter of around 77.14 millimeters. As for the module, M is going to be equal to the pitch diameter divided by the number of teeth. So it doesn't matter either way, I can take the pinion or the gear, but either way, I'm going to get something around 6.43. So now we can start to draw in the pitch circles. So I got a center distance of 90 right there, and I'm going to start to fill in each of the pitch circles. Remember that they need to be tangent to each other, so they're going to meet at that pitch point. So now let's calculate the addendum and dedendum. A is usually just going to equal m, so that's just going to be 6.43 millimeters. And then as for the dedendum, d subscript d, that's going to equal 1.2 or sometimes 1.25 multiplied by m for a bit more clearance. In this case, we're going to get 7.71 millimeters. We can now go ahead and draw that in. At this time, we can start to divide our pitch circles into the number of teeth we have. So our gear on the left here has 16 teeth, and I'm just going to bisect everything with a compass. If you need help bisecting angles with a compass, I'll leave a video tutorial in the description. As for dividing the pinion into 12 teeth, you can adjust your compass to the radius of the pitch circle and use this to mark 60 degrees from wherever your compass is rooted. And using this method, you can divide your circle into 12 teeth. Our next step is to find the base circle so we can create the involute teeth. To do this, we first have to find the base pitch. And as a reminder, that green circle in the diagram, that would be the base circle in our context of making gears. Another defining factor of the involute curve is this angle alpha formed by the tangent line to the curve. To find the base pitch, we have substeps 2 and 3 that we first need to complete to find the base circle radius, RB. My formula for base pitch, PB, is equal to pi times m cosine of alpha, and we want to find what this angle alpha is going to be. So I've got this long formula for the length of action A, and I recommend just plugging it in, but the r's are going to equal the radius of the pitch circles, and the subscripts P and G correspond to pinion or gear. So when I plug this in, I get something around 24.58 millimeters. Now, MP is my contact ratio right here, and you notice the formula, I can plug in my length of action. So the contact ratio is the average number of teeth that are in contact with each other at a time, and in general, we definitely want this to be greater than 1, but an ideal contact ratio would be around 1.4. So let's first rewrite A over PB as A over pi times m cosine of alpha. And now let's solve this as the equation for alpha. So 1.4 equals A over pi m cosine of alpha. Cosine of alpha is equal to A over 1.4 pi m. That gives us inverse of cosine of A over 1.4 pi m. That's going to equal angle alpha. And when I plug all of this in, I get something around 29.62 degrees. So we found angle alpha, and we can plug that into our base pitch formula, and we're going to get something around 17.56 millimeters. But we want to find the base circle radius, not just the arc length. So PB is the arc length, RB is the radius. We know that the circumference of the base circle multiplied by theta over 360, since we're doing this in degrees, that's going to equal PB, the base pitch. So let's go ahead and simplify this down to pi RB theta over 180 is going to equal PB, and we can flip that around. So RB is equal to 180 PB divided by pi times theta. And now we ask, what is theta in this context? So what is theta? That theta in this context is going to equal 360 divided by z, the number of teeth. So let's go and plug it in. RB is equal to 180 PB multiplied by 360, 1 over 360 pi divided by z. And eventually all of this is going to simplify down to PB times z over 2 pi. Now we can use this formula to actually solve for the base circle radius of both of our gears. So for RB1, we're going to get something around 44.71 millimeters. And then for the pinion, we're going to get RB2 is equal to something around 33.53 millimeters. Now we can draw in the base circles. Afterwards, I've drawn this vertical line here, that's the direction of velocity of the teeth, and then I've drawn this other line with the pressure angle, 25 degrees, that's called the common normal. Now the line that is perpendicular to this that also goes through the pitch point, that's going to be called the common tangent, and you can use it as a guideline later to draw your involute teeth. Now I'm bringing in this hideous contraption to draw the involute teeth. Remember that an involute curve is just like a piece of string wrapped around a circle, in this case a strip of paper. I'm lining up the mark I made on the paper with the pitch point, and as I wrap this strip of paper around the base circle, I can trace out the involute curve. Now I'm using a compass to bisect 1/16 of the gear in order to determine the tooth width and tooth gap. In this case, they're going to be equal since we're cutting these out by hand. Using that intersection point, I'm going to do the exact same thing and trace out the involute curve. Afterwards, I created a template of the tooth with cardstock. Notice that I traced the pitch circle so that I could properly line up the template as I traced the rest of the teeth. I repeated this process with the pinion. I later glued the template on a piece of cardboard and cut out the gears. To see if the gears actually mesh, you can try to put them together and see if the pitch circles line up. Thank you for watching. If you have any questions, suggestions, or corrections, please put them in the comments.